Oh, good evening, everybody, and welcome to the first Sigma meeting of 2022. For those of you who don't know me, my name is Pete Sherman. I'm the chairman of Sigma, and I'll be your MC for the evening. I'd like to start by welcoming not just the Sigma members tonight, but also our affiliated club members as well, club and society members as well. That'll be Haz, Aberdeen, Ken Gorham, Caithness, and North Honestly. And any first-time visitors and guests we may have, along with us for the ride tonight as well. And a very warm welcome to our two new members, Derek and Tricia, and returning member Mike Reed. It's so nice to have new members this time of year. It's quite warming, and it makes us hopeful that it means we're doing something right. And Mike, welcome back. We're glad to see you back with us again. While we're on the subject of membership renewal, don't forget, if you want to take advantage of the 50% off of your membership renewal, that has to be done by the 31st of this month. So if you can get the money to Mick, either by check or by bank transfer, preferably by January the 31st, that'll be great. Otherwise, you're gonna have to pay full whack. Okay. Before I go any further, I must make an official apology. In this month's newsletter, I said that Mick had put together a handy winter sky guide. As soon as I pressed the send button on that, I realized, I'm sure that's the one that Bill put together a few years back. Soon after, Bill emailed me saying just that. So sorry, Bill, my mistake. Nothing to do with Mick. Don't blame Mick, blame me. If you've not read that yet in the newsletter, please do so, as I recommend it, because it's full of useful information put together in Bill's unique and easy to sort of unique and easy to read style. Okay. Right, having me in the background tonight, we got Rich and Mick, who are the Zoom co-hosts. They'll keep everything running should anything happen to me technically. Any technical failings at all, which touch wood hasn't happened yet. There's a wardrobe here, believe it or not. I really can't see it. Also in the background, we've got Stuart Brooks, who's going to be giving us the space news in the second half, and along with Mick, who'll be doing the morning sky at night, showing you what's up in the night sky this month. And also joining us from English here is Chris Stradding, who's going to be handling all the questions and answers. Okay. So the Zoom controls, for those of you who don't know, just don't go through these a little bit quickly, because I say we've got some new members. If you have any questions for our speaker, please put them into the Q&A. You'll see a little Q&A pop up on your toolbar. Okay, just press that, put your question in. Chris will keep an eye on them and ask them to Juan at the end of his presentation. Okay. The chat is open at the moment, so you're able to chat to everybody. And during the actual presentations and that and the talks, the chat will be turned off, because it just makes it, when these pop-ups keep coming up, it makes it a little bit sort of distracting for our speakers and that. Okay. And so don't put your any questions in the chat. Please put them just into the Q&A there. If you have any issues at all, you're not sure what's happening, and you want to contact any one of us here on the panel, just click the raise hand button. We'll see that's up, and one of us will contact you to see what the problem is. Okay. Okay, just let you know before we go further that after this meeting, we're having the members gathering. You should all have the link in the newsletter, but Rich will put it up into the chat at the end of this meeting. Okay, so the probably easiest way to do is just click that, and it should take you straight over to the other meeting. You've got to give us a couple of minutes to shut this one down, but then we open that one up. Okay, that's the chance for us all to get in, and Juan said he's going to come across if he can, if his 11-month-old child sort of lets him. But you try and pop in and say hello, so we'll have a chat to him and ask any questions maybe that you didn't have the chance to ask during this meeting. Okay, so the meeting brief, the way it works is that we have a main talk, and then we'll have the questions and answers with Chris. We then have our 10-minute break. Chat will be back on for then, so we can have a chat with everybody through the little chat room there. After the break, members photo. I say photo, so I've only got one again this month. Space news with Stuart Brooks, Morning Sky at Night with Mick, and then a little bit of club news from myself. Okay, anyway, tonight we'll be taking a look at echo mapping of supermassive black holes with Juan. Juan was an undergraduate in mechanical engineering at UNMA. I should have looked at what that was, in his hometown of Mexico City. Afterwards, he finished his master's in science at the Institute of Astronomy at the same place. Then he emigrated to the UK, where he obtained a PhD at the University of Southampton, working on multi-wave observations of neutron stars and white dwarfs. After he worked as a postgraduate researcher at the I'm going to get this wrong, Pannenkoek Institute, University of Amsterdam. It's them Amsterdam ones always get me. I don't know why it is, and the Dutch ones. He later came back to the UK and researched the Fellow of University of St Andrews in Scotland, working on supermassive black holes. He's a lecturer in astronomy at St Andrews. Juan joined us for a practice session on Sunday night when he'd literally just gotten off a plane back from Mexico, noticeably jet lagged, I was told by Rich. So Juan, I would like to thank you for doing that for us and giving up your time for doing that. And also, I would like to thank you for giving up your time tonight to give us a talk. And would everyone please welcome Juan Santisteban. Over to you, Juan.
Thank you very much, Pete. Yeah, so I'm just going to start sharing my screen and put up my slides. Yeah, thank you very much for the invitation. Unfortunately, we aren't able to meet up in the north of Scotland, but I would have loved to be there. But in any case, I hope that you're going to have a good time talking about a little bit about my research of what I do at the University of St Andrews. So the specific topic that I would like to share with you is what I've been doing to study supermassive black holes in the nearby universe using a fantastic technique called echo mapping or reverberation mapping. So before we go deep into what actually I do on day-to-day basis, I just want to talk about the overall picture of why do we care about this. So you've probably seen this photo at some point in your if you're any astronomy curious around. So this is the extreme deep field taken by the Hubble telescope, Hubble Space Telescope. So this is one of the deepest, most that peer back into time. It's the furthest image that we have of the universe. So every single point that you see here is a galaxy, and they're incredibly bright, and you can see there's a lot of them. And what we come to realize in the last 50, 60 years, or even more, is that at the core, at the center of almost all of these galaxies, lies a supermassive black hole in the middle. These supermassive black holes are incredibly important because they, since they are in every single galaxy, these supermassive black holes grow and evolve through the history of the universe along with the galaxies. So the two are inevitably interconnected. And here it's some very nice, one of the latest simulations, like cosmological simulations, everything done in a computer, on how we think the universe evolved and grew after the Big Bang. So you could see the intricate networks and the cosmic web just pulling matter together and accumulating into these nodes, and eventually forming stars, forming galaxies. What is very important is that many of these already had black holes, maybe formed at the very start of the universe. And what is critical is that these supermassive black holes, even though we think of them, they are extremely massive and huge, they're actually really, really small in comparison with the galactic scales. And what you can see now starting to blow off as this sort of like gas coming out of these nodes, it's actually feedback, it's actually material being blown off from the supermassive black hole. So it's just quite incredible that something as small on the universe scale as a black hole can have a massive influence very far out of where it resides. So this is why understanding supermassive black holes are critical, because these inevitably inform and affect how the universe grows throughout the cosmic time. So we need to understand how material comes close to the black hole, and then how eventually some of that material goes in and some of it goes out, impacting and filling out the whole universe with hot gas and other phenomena that we'll talk a little bit about that. So the one question that I would like to tackle through the rest of the talk is just this: how do black holes feed, and how, in particular, how do supermassive black holes feed? And hopefully by the end of the talk, we will have a little bit of an answer. At least we're attempting to understand how this is actually happening out there in the universe. So let's try to see what we know of, right? So here is a beautiful image from M87, beautiful elliptical galaxy, and at the core of this lies an incredibly massive around a billion times the mass of the sun supermassive black hole. And you can see, right, that even in this image, you can see that there is a tiny little strip, a jet coming out. So that is material that is coming out from the center of the galaxy, from the supermassive black hole. And it's incredible, right, that this jet, particles that are being accelerated almost to the speed of light, are almost the same size as the galaxy itself, right? So this is just another point towards the evidence that these massive black holes influence not only the parts that are close to the black hole, but further out. And in almost 3 years ago, this particular galaxy was target of a very clever experiment using sub-millimeter telescopes all around the world, from Greenland to the Antarctica, from Hawaii, Mexico, Chile, all around the world. So combining the power of all the different telescopes to try to image the black hole shadows, or where the black hole lies at the center of this galaxy. And this is one of the famous images that came out of that project from the Event Horizon Telescope. So this is essentially one of the first image of a black hole. And we have an idea, right? So all what you're seeing here is you have material that is coming out of the black hole, very, very, very close. And what you see is the shadow is just where the black hole itself lies. So this is sort of like an animation of what we sort of expect that is actually happening, right? So you have the massive black hole, and you have material that is flowing into the black hole. But this process is not random. It doesn't come from all places. Most of the time, this material actually starts to lay down in a plane. So the material settles down, and just like a donut around the black hole starts swirling around. And eventually some of the material starts drifting into the black hole. And part of it gets sucked into the black hole, but a lot of it comes out in these powerful jets. And it's on the base around these jets that we observe, the material that is going out from this picture of the supermassive black hole was observed. So one of the things that we want to understand on the big side is, how do supermassive black holes feed, and how do they affect the evolution of the universe, of the galaxies, and how to link that to the tiny little scales where this process is actually happening. And for that, we need to sort of understand what's the structure, how exactly material is funneling in, right? And that is a very hard and challenging job. So here you have an animation, right? So in the past animation, we saw that was an actual simulation of the black hole. This is just an animation, sort of like an artistic impression. But in that past simulation, we were focusing only on the tiny little bit, very, very close to the black hole, so just a few times the size of the black hole. But as we know, these supermassive black holes actually have influence further out, and it's actually a lot more structure further out from the black hole itself. And all of these parts are combining together into powering these incredibly bright sources in the sky. So usually at these supermassive black holes, when they are continuously sucking material into them, accreting material as we call it, we often call them quasars or active galactic nuclei or AGN. So throughout the talk, I'm probably going to be interchanging all those words I'll try to sort of stick to AGN, but they all sort of mean the same thing, right? So they are black holes that are actively sucking material into. So one of the key challenges is try to dissect and the structure of this very complex system from observations, because these observations, you have material flowing in, you have material flowing out. It covers a very broad range of scales that you need to resolve. So things very close to the black hole and things that are very, very further out. Things that can change within a few hours, and then things that can change on centuries timescales. So it's a very challenging problem, not only because we as researchers have only a finite time to do these observations and these experiments, but also the experiments itself. It requires a lot of different telescopes on space and on the ground. And what this structure we think it looks like, it has these sort of vaguely 5 different components. So at the core of it, you will have the central mass, the supermassive black hole. Around it, you will have this sort of donut-shaped material called the accretion disk. So just like a pancake that it's continuously feeding the black hole. As you go further out, material starts to go off a little bit off the plane where the accretion disk is blowing, is swirling around, and you have this sort of fluffy region called the broadline region. We'll talk a little bit about that. Then even further out, as the material gets colder and colder, so that the closer you are to the black hole, the material is really hot. It can go up to millions of degrees and usually will shine in X-rays. But as you start going out, the material gets cooler, so you can get up to the way to the torus. So it's a very dusty torus with temperatures of a few thousand degrees. So it's very puff up at the edges. And on sort of perpendicular to this system of three things, you can have a jet coming up almost perpendicular. So this is material now outflowing from the system. And these jets can be as big as the galaxy itself. And then a narrow line region, which is also some other clouds that are even further out. But all of these are related gravitationally to the AGN in some way or another. And for some of these components, they're actually very easy and very spectacular to observe, like the jet. So this is a radio jet, so an image. So it's a Hubble image with, though you can see the galaxy itself, and the jet is observing the radio. So you can see these beautiful bubbles just being created by material being blown off from the supermassive black hole in the center. So this is very easy to observe, right? The jet, they're very massive. But as we try to go in and go closer to the black hole, things get harder to observe. So maybe even you can do this with the Hubble Space Telescope, where you can observe this dusty torus and you can actually see their little donuts. So this is an actual image from the Hubble Space Telescope of this torus around the supermassive black hole, and you can see the black hole at the center on the sort of like the zooming right panel. But the torus is still quite far out, right? And what I'm really interested in is really that part, that very close part where the accretion disk starts to plummet into the black hole. But unfortunately, we don't have the technology to observe that directly. This accretion disk is just too small and it's just too far away from us to be able to observe it. If we would try to do this, we would need sort of like the Event Horizon telescope, but just 1,000 times bigger. So we would need to start putting telescopes on other planets and then somehow sync these telescopes in order to be able to start resolving this. And this is tough, and at least probably not in my lifetime that we will be able to see this. So we have to come up with ways to overcome these limitations. And there are ways. So what we try to, the next part of the talk, I will try to actually talk you all through on how we actually do this, how we actually see and deconstruct the part that is very close to the black hole. And to try to answer this fundamental question, I will try to subdivide it into 2. So the first one is to know how massive these black holes are. And the second one is how fast they are fitting, because then you would know the two important things, right? So how big they are and how bigger are they getting as time goes by. So I'll try to talk with the first one. So how do we weigh a supermassive black hole? Yeah. And the answer to this question is echoes. And you probably know this concept already, right? So this is how we measure, for example, how we use sonars to measure the depths of the sea. We physically cannot go and measure the topography of the seafloor, right? It's just unfeasible, and it would take us a long time to try to do this by hand. You have to go there and physically measure, and how do you measure it, right? But one of the ways that you can do it is just taking into account that the sound takes has a finite speed, and can travel all the way from the boat all the way to the seafloor and go back. And if you record that time that it takes to go down and up, because you know what the speed of sound is, you would immediately know what is the distance to the seafloor, right? And this is a very efficient way of doing it, and non-intrusive, right? Because you're making the signal do the job for you. You don't need to actually go there. So how we do it in astronomy is we're trying to apply the exact same principle. Let's try to do a signal that allows us to track all these different components and measure and let us deconstruct the structure around the supermassive black hole. But instead of sound, we have to use light, right? And that is the only thing, and that's what we can do. Use light in order to use it try to use light echoes with around the black hole in order to sort of deconstruct how it looks like, just like the sound, like sonars do for the seabed. So then how can we take this advantage of this principle of an echo, of a sonar, and weigh a supermassive black hole? And for this, I'm gonna put one of my so it's gonna be it's a very easy concept. And the thing is, it turns out that once we start looking at these supermassive black holes, we notice that there is gas that is orbiting around the supermassive black hole. And if a gas is orbiting, it must be in equilibrium, right? So they must be maintaining a certain orbit. So that means that they must have a speed around it, right? Just like the Earth is just going around the sun. So one of the things that in order for you to be in orbit is that the kinetic energy of how fast you are moving has to be equal to the gravitational energy, right? Otherwise, if you are going too fast, you would just go away. Yeah, you would not stay in orbit. You would just fly out from the supermassive black hole. And if you have very little energy, the gravitational pull of the black hole will come towards you. But if these clouds are in equilibrium going around, then these two things can be equated. So that means that if we can find some echoes, so somehow find an echo of a light emitted very close to the black hole being echoed in these clouds, and if we can observe this echo, we could sort of measure what is the sort of like the distance between the supermassive black hole and these clouds at the edge of the AGN. And if we know that, on top, in addition to how fast these things are moving, then with these two things, with the radius, with this distance between the clouds and how fast they're moving, they give us a scale. We can just multiply those two numbers, and will give us right away the mass of the black hole. And this is one of the two equations that I have on my whole presentation. So we'll try to see how we actually do this. So the first point, right? So we need two things, right? So we need the distance between the supermassive black hole and these clouds, and how fast they are moving. So let's try to find the first one. So how far they are. And one way to do it is to find the echoes. And what we do this is, so one of these experiments that we have been doing this for a long time now is with the Slow and Digital Sky survey. So this is a survey that is scanning around 800 quasars, trying to find echoes between the broadline region, between the lines, and the light close to the black hole. So you can see, so here's an example of one of these. This is actual data that we get from the telescope. And hopefully you can see that the two, these two lines, these two light curves that you see, so you have time versus intensity on the y-axis. So these two lines are actually shifted by around 60 days or so. So that means that the black hole and the clouds are around 60 light days away from each other. Sorry. And you can do this for essentially any single AGN that you have in your field. So for this one, we have that around 60 days. And then how can then we get how fast, right? So 60 days times the speed of light, that will give you a sort of like a physical size in kilometers. And then how fast it is moving. And it's really sort of easy to get. This is the easiest of the measurements. Because you can relate you can look at this line that is originated in the broadline region, and make use of the Doppler effect. Because the Doppler effect, what we'll do is we'll redshift or blue shift the line, depending on if it's coming away or coming towards you. And depending on how fast these clouds are coming, it's going to make a line that is very narrow, is going to spread it out. So the broader it is, this line, as we measure it, for example, here in the bottom panel, the broader it is, that means that the broadline region is going very, very, very fast. So this is a very easy measurement to do. So you just go take a single spectrum out of this AGN, and you can measure that width, and that will give you the velocity right away, just by doing the Doppler effect. So with those two measurements, right? So you can measure this echo, and you can measure this line, then you can weigh the mass of the black hole. And with this experiment, we have now over 200 of these masses of black holes. So you can see so all of these red points and black points are masses that are from the Slow and Digital Sky survey from just a couple of years ago. And you can see, right, that we're weighing black holes from 10 million to over 1 billion masses, all the way to redshift 2, which is sort of like a quarter of the age of the universe. So with these experiments, we're not only measuring how, and we can measure then how massive these black holes were back in time. So this is very important, because by measuring the masses of these black holes, it tells us how more massive they were in the past and how fast they should have been feeding material in order to become the black holes that we observe in our local universe. So hopefully that answers the first question on how massive are these black holes. And the second question is how fast they are accreting. And we're going to be using the same technique, just the echoes. But instead of using the broadline region, these fluffy clouds at the edge, we're going to be using the accretion disk itself that is very close to the black hole. And this is the other equation that I have. But it turns out that if you can measure these echoes between different filters that you use in your telescopes, between different bands, the echoes, that the size of the echoes that you find are directly related to the mass of the black hole and how fast it is feeding. So in broad terms, it means that if you can follow an AGN and you can take images consistently in different filters, so in the blue or in the red filter, if you can follow those how the AGN varies through time, and you measure the shift between these light curves, then that alone gives you a measurement of how fast the material has to be coming in. So this is a difficult thing, because if you remember, if I just go quickly back to this, right? So here, remember that the broadline region is further out in the black hole. So here you need around 62 days for the light to travel all the way from the supermassive black hole to the broadline region, get echoed there, and then we observe it. 60 days, right? So that means that if you miss a couple of days, so you're trying to observe it as much as you can, but if you missed a couple of days, it's not much of a problem because the lag is almost 60 days, right? So as long as you take a few down the line, it should be fine. But the accretion disk, remember that is very small in comparison. So the light time travel inside the accretion disk can get very small. And usually this is around a few days. So you can go all the way from the supermassive black hole to the edge of the accretion disk within a week. So it can take almost a week to go all the way out. And usually you try to measure things in between. So the delays, the lags that you observe, the echoes that you observe are usually around days or so. So that means that you need to consistently observe almost every day or even several times per night to do that. And that is already a hard problem, right? Because usually you usually go to an observatory and spend a few nights there, take observations, and then you go back, right? And you cannot use a telescope anymore. So how can you overcome this problem in order to tackle the science question here? Before that, just what you would do. So essentially, what would we expect, right? So we're trying to measure these echoes from the disk. So what would we expect? So I think as I said at the start, right, as material tries to come inwards towards the black hole, it starts to heat up. So material that is very close to the black hole is around 1,000,000 degrees, so it shines in X-rays. But as you start going further out, the material is a little bit less cold, so a few tens of thousands of degrees. So you start shining in the ultraviolet, and then as you go down, it starts going down in temperature and the optical and then infrared and so on and so on and so on. So you would expect that the hotter parts of the accretion disk to have echoes with shorter delays, right? Because they're just closer to the black hole, and the echoes from the edge of the accretion disk should be observed in redder wavelengths, so with cooler temperatures, so closer to the infrared. So we would expect. So the expectation is that larger lags that occur at lower temperatures would just be longer. So we have been trying to. So people have been trying to do this. I haven't. So I've just been doing this for maybe 3 years now, three and a half years. But one of the first attempts to do this was back in 2007. So this is for a very famous galaxy, NGC 5548. And you can see there, so what this plot, I'm just going to explain this plot. So this is what we call a delay spectrum. So you have wavelength on the x-axis. So it tells you the energy of what you're observing. So all the way, I think is like U filter all the way to I filter, very close to the near infrared. So the first few attempts of doing this, it was just using several telescopes and asking people to try to get as many images as possible from different sites and try to combine them together. And you can sort of see that the longer wavelengths, so the ones on the right, have a longer delay, right? So it's sort of with the expectation that longer lags occur at larger wavelengths, which lower temperatures. So here was one of the first evidences that maybe we can actually measure how fast these how fast are these black holes feeding. But it was very tentative, and it's, as you see, it's a hard measurement. But in the last decade, things have been improving significantly. So this is the same experiment but 10 years later, using the Hubble Space Telescope, the Swift X-ray telescope, and ground-based telescope. And you can see very clearly, so this is sort of like the same plot, wavelength versus the time delay, this versus the echo delay. You can see that there is this nicely smooth increase from shorter wavelengths to longer wavelengths and increasing, right? So that means that the disk is hotter and at the close to the black hole and gets cooler out, and it takes roughly around 5 to 6 days for to the edge, almost to the edge of the accretion disks. So the disk is around 6 light days across. And after this, there's been a lot of attempts at trying to build upon all of these results. And one of the main ways to do that is with the Swift X-ray telescope, which is a very versatile space telescope from NASA that it's very quick. This is why the name of Swift is very quick to move around to target. So it's very efficient at when you try to use it. So this way you could track many AGN almost daily. And this is one of the first experiments to try to do this consistently over 4 or 5 different AGN. But as you can see, right, that even though the data has been presenting the same sort of like the same trends, there's still like the data doesn't look entirely convincing, right? And furthermore, getting space telescopes to do these experiments is incredibly hard. You need to compete against the whole world to get these experiments done, and it's very expensive. You can only do a very few at a time. So how can we do this in a much cheaper way and try to cover as many AGN as possible? And this is where the Las Cumbres Observatory robotic global telescope network comes, right? So this is a network of around 20 telescopes all around the world that you can use robotically. So there is no intervention from a human. So the only thing that you need to do is tell the telescope, tell the system which object to observe and with how many, on what filters do you want to observe and for how long. And that's it. And then it will automatically schedule it across it. So in this way, we could actually do a lot of different targets for a longer period of time without us having to go physically to an observatory. And even better, right, is that because they have several telescopes in the north and several telescopes in the south, you could actually take more than 1 image per day for every target, because when in Chile is day, it's probably going to be night in Australia and the other way around. So in this way, we've been able to do daily and sub-daily monitoring of AGN, providing one of the best light curves in the world for this AGN. And in combination, what we try to do in the last couple of years is do both things. Use the Swift X-ray observatory that can observe in X-rays and in ultraviolet, which we cannot do from the Earth, and use Las Cumbres Observatory to do all the optical monitoring. So if you combine these two things and you try to observe daily for a year, then you can actually go and test directly how fast supermassive black holes do, how massive supermassive black holes grow. And this is what we did with a galaxy called Ferrel 9. And what you see here is a video of 1 year of data in around 11 bands. So this is all the way from the ultraviolet, taken with a Swift X-ray telescope on the top, all the way going down into the blue colors, green colors, all the way almost to the near infrared already down here. So that is the so that is just completely 1 day of data. This every single point is 1 observation on one of these telescopes. And you can see, right, that all the data looks correlated, right? So what is happening in the ultraviolet seems you can see almost the same wiggles all the way down to the other wavelengths. But if you are keen on your maybe on your eyes, and if you stare at this long enough, you will start to see that that actually the light curves are sort of shifted around, right? So remember, we expect that we are gonna see longer lags at longer wavelengths, so that the ones in the bottom should be shifted to the right a lot more than the ones on the left. So I'm going to try to focus on one of these features so that it's sort of easy. So you can see that even on the data, it's there, right? So we're going to focus on the bluest one, so taken with Swift. You can see that peak, right? And we just go down through all the different light curves. You will start to see that gradually that little peak is starting to move to the right a little bit, a little bit, a little bit, a little bit. And if you try now go and find where that peak is in the bottom light curve, so all the way to the near infrared, you will see that it's clearly offsetted from the one in the top. So this is that time delay. This is an echo. That is that you are looking. You're seeing how the light is traveling even further out. It's echoing at a distant part of the disk, and this will allow us to measure that size and how fast it's fitting. So it turns out that from the ultraviolet, so from the zone that it's emitting ultraviolet in the disk, all the way to the part where it's emitting all the way in the infrared, there's about 8 light days of the size, right? So it's an incredibly massive accretion disk, right? Try to compare it with things in our solar system. I have a little slide after this. So if we look at these lags, right? So instead of just sort of looking at one by eye, if you actually sort of try and measure them correctly one by one, you actually see that they increase very, very smoothly, all the way from the bottom all the way to the top in around 8 days. And this fits very, very nicely with observations and with theory. So this is sort of what we expected the NGN to be doing in the first place. So in the end, just to sort of like a comparison so that we can see how big this is, right? So the size of the accretion disk is around 8 light days, but the furthest thing that the humans have put out there, it's around 20 light hours. So, right, this is not only I think Voyager 1 might be close to 1 day, one light day. So this disk is almost 8 times bigger than the whole solar system, which is ridiculous. I find it incredibly mind-blowing. And just a little bit of comparisons, right? Where the Earth is only 8 light minutes away from the sun, this size is 8 light days. And by using the theory and measure and retrieving the information from these different lags, we can tell that the black hole is roughly eating around 1/10 of the mass of the sun every year. Just that amount of mass that it's flowing through the disk is most likely all going into the black hole, with a certain fraction trying to maybe go out in the form of a jet. And just so that you know, right? So what I have presented to you down here is only 1 year, right? So we're following this down now. This is a plot that I took. This is the latest plot that we have. This is 4 years of data. So we have been following this AGN for 4 years, 3 times per day. So every time it goes above Chile, South Africa, and Australia, we take an image. So this was just like the last one just was a couple of days ago. So today in the morning, we should get the new images from them. And even though, so we have proven now that we have, our technique works, that it's a fantastic way that if we use robotic telescopes, we can measure very efficiently this, how well do these supermassive black holes feed. So I'm the principal investigator of a key project with Las Cumbres Observatory to try to monitor many more of this. So around 15 new targets. So I have this little plot there. So the ones that we have done in one way or another are the filled circles, and the ones with triangles are all the targets that we are aiming to do in the 3 years of this running project. So we're now we're finishing now we're going now through half half of the project now is already undergone. But on top of that, we have a lot more data because we have been taking data almost since 2014, not as intensive as we have had in the last few years. But in total, like the images that I have on my computer at the University of St. Andrews that I have analyzed, we are almost at the 200,000 images mark. And that represents a total of 300 days of observing, of pure observing that we have done in almost a decade. So hopefully in the next few years, with over 4,000 hours of telescopes, of hours in these robotic 1 meter telescopes, we will be able to decipher a lot of them. This is just a little preview of what we've been doing in the last few years. So we are running an incredible experiment with the Hubble Space Telescope, even though it has had its trouble in the last few months, and I could talk a lot more about that if anybody has any questions. But we're using Hubble Space Telescope, SWIFT, and Las Cumbres Observatory, and making this. I'm trying to track this supermassive black hole, and we're doing it in a lot more. And just so that you can see that even though, for example, on the left part, like everything seems to be smoothly, not every AGN. Not every black hole is behaving the way that we think it's behaving. So there are a lot of uncertainties, a lot of things unknown still yet to be discovered. But this is one of the first times that we've been able to do this consistently. So I think with that, I will almost leave my talk and maybe open for questions. Just gonna leave you with my conclusions. So hopefully, I gave you at least a teaser, and hopefully you get the idea of why it's important to understand black holes and how supermassive black holes grow through cosmic time. Hopefully, I also convince you that using echo mapping and using multi-mission experiments with SWIFT or Las Cumbres, they're providing new and state-of-the-art data that will allow us to understand what is happening very close to the black hole. Try to measure its mass and trying to measure how fast they're feeding. And this example of Ferrel 9 is our flagship example. We have proven that it works, and it works really well. So hopefully this key project that will give 18, I think we're probably gonna do more than 15 by the end of next year. We'll probably advance the field quite a lot. So I leave you there with my website if you want to know a little bit more about that. And with that, I'll take questions. Thank you very much.
That was fantastic, Juan. Absolutely brilliant. Okay, Chris, if you're there, we'll hand you over any questions you might have. If anyone's got any questions, just pop them in the Q&A now, and Chris will pick them up.
Yes, first of all, I'll just back up what Pete said. Thank you very much. Fascinating. I have one quick question. I might have missed it in the project. In the presentation. You mentioned in the project that it will be delivering 8 more targets. How many have you been studying in the project so far?
Yeah, so I think we have at least done 12 by now, at least. So not all of them have the grade. In fact, I can show you. You can still see my screen?
Yes.
So because this is all robotic and we have so many images, I don't see all the images by myself. So I have made my computer make all of this. So I have this little website where I track. So these are all the AGNs that we're tracking at the moment, the ones that said observing. And we're receiving images from them daily, or almost daily, depend. And some of them are really nice, right? So like the one that I showed you here for 09. But some of them we're just starting to observe them. So this has only like a couple of months. But we have data on almost 55 targets. Not all of them they have the best data to do all of these experiments. So we expect, at least I expect, that at least 15 will have a complete full data set where we can test this.
Cool. Thank you. There's a few questions come in. There's a personal question that's come in from Rich. He just said, what motivated you to get involved in this field of research?
Well, I I have studied, so I did my PhD on neutron stars and white dwarfs. But what I really like and is the process of accretion, this process of material getting into the black hole or the neutron star or the white dwarf. It turns out that that process is universal. It seems to be that it doesn't matter what you have at the center. It always follows the same, sort of like the same physical laws. So it was just this opportunity to do these sort of experiments in St Andrews that got me over here to Scotland. And this is why am I doing here? I still work on neutron stars and white dwarfs, but I spend most of my time on black holes now.
We might be able to get two questions in one here, actually, because I've got a question, another one from Rich. He said, what are the escape velocities of the jets? And then there's a question from David Ray. What determines whether matter gets thrown outwards or is sucked into a black hole?
Yes, so the escape velocity are a few thousand kilometers per second. So we observe this. It's on 1,000 of kilometers per second, the escape velocities of these things, and it depends where are they being launched, right? So if things are getting launched further out, then you don't need that much velocity. But things that are very close to the black hole, they can reach speeds very close to the speed, so a few percents of the speed of light. And this is what we observe in jets, for example, that they go very, very close to the speed of light.
Copied. Another couple of questions. How big does a black hole have to be supermassive? And does every black hole throw material out?
So the second question is, yes, every single black hole that we observe throws material back out. So one way or another. Because you have magnetic fields. So the key thing here are magnetic fields. So the material that is sort of going around the black hole is creating magnetic fields, and some of them get these magnetic fields can get sort of like a spring. They get compressed, and when they release that energy, they flow out. And we have seen this in stellar mass black holes in our galaxy, so things of maybe 10 solar masses, all the way to things with 1 billion solar masses. And the second part was how
big does a black hole have to be to make it a supermassive black hole?
I think the cutoff so we start talking about supermassive black holes, things that are close to 1 million solar masses. Below that, we sort of classify it very arbitrarily as intermediate mass black holes. But at the moment, we don't know of that many intermediate mass black holes, right? So we know a lot of stellar mass black holes. We know a lot of supermassive black holes, but the things in the middle, they're more elusive. We haven't really found any. There's few candidates for them, but that is an open question in astronomy. Just like how to make a supermassive black hole,
right?
And yeah.
Question from the chairman, from Pete. It is said that time moves slower the closer you get towards the center of a black hole. Does this have any influence on the observations you're making, and does it affect the wavelengths of the light that you're viewing?
No. So because fortunately enough, let me see where it's it. So it's really when you get so a few sort of like a radii of the black hole, that's where general relativity and its effects will be most influential on the light that you see. So that's where you start bending the light, but what we observe is further out on the accretion disk, and there all these general relativistic effects are almost negligible. So it almost follows Newtonian, so like the Newton's law without getting into general relativity. So thankfully, because otherwise it would add some more complexity to it. But if you can do the same experiment just on pure X-rays, on things very close to the black hole. And there are teams that are starting to do that. And there you have to account for light bending and how light warps around the black hole, and then how it hits the accretion disk, and then how it looks up. Yeah.
So Neville Brown has posted a question. How far away are the black holes that you are looking at?
So these are a few hundred megaparsecs away. So the closest one is, I don't remember. So this is why this is very neat. So this is the redshift. This is the closest redshift quasar that we have. So 0.001. I don't know how many megaparsecs that is, but technology calculator. 4 megaparsecs, almost 5 megaparsecs away. That's the closest one we've done so far.
Okay, thank you. From Tim, are there any plans to build more 1 and 2 meter robotic telescopes in the northern and southern hemisphere in order to increase the number of observations?
Yes. So in fact, they have just opened 2 new 1 meter telescopes in the Canary Islands on Tenerife. They just opened a few months ago, and that has increased massively our coverage in the northern hemisphere, because we only had 1 meter telescopes at McDonald in Texas, and yeah, so there is that one, and then I think the next one that is planned is on Tibet.
Okay.
Yeah.
Interesting. From Karen Fullerton, are there any other parallels in life stroke the universe that are like black holes?
Are there any other parallels in life that are like black holes?
Any other things like black holes that are potentially for future investigation, maybe once we've finished studying this area?
Well, if there is anything else that we can apply this to, this technique, sort of.
I guess so. Yeah, try that.
Yes. So you can. So this echo tomography can be applied to essentially almost anything, right? You can apply it into white dwarf systems. You can apply it in neutron star systems. Yeah, I'm trying to think about any other sort of. Yeah, I'm not entirely sure. Yeah, I'll have to think about it. Maybe with a beer later. That will.
Well, we can maybe chat about that in the event after the meeting's finished.
Yeah,
exactly.
exactly.
Get together.
Yeah.
And we have one last question. So if anybody else has any questions, now is your time to chuck them in the Q&A box, please. But from Bill Graham, a challenging talk. One, thank you. How does your new knowledge affect your understanding of how the future of the black hole develop? Does it just get bigger or jet out more material?
Yeah, so how does your knowledge affect? Yeah, so one of the things that we are that we have been finding is that these outflows of material influence a lot more than we thought of possible. So we're finding that almost every time that we think that we're looking at the pristine accretion disk, just getting material to the black hole, there's almost always some kind of fluffy thing going out that it's throwing us away, and that it's making the inferences that we make from our observations harder. And I think that is, and what it does, it affects these measurements of how fast and how big they can get. The other thing that we are currently very looking at is trying to see at the black holes that are feeding the fastest, right? Because one of the major problems that we have in astronomy is that when we look back in time, for example, in the Hubble Deep Field, we see supermassive black holes, and we see them all the way back to just a few 100,000 years after the Big Bang. And they are already massive, right? So they're already millions of times the mass of the sun. So the question is, how do you make them so big, so fast? And that is currently a question that we don't have an answer to. There's several sort of ways on how to get around it. Maybe so we're trying to. So one of the new things in this key project that I'm leading is trying to target this highly, we call highly accreting, right? The fastest eating black holes, to trying to understand how they are actually doing it and see if there are any clues there on how we can extrapolate to the early universe and see if there is anything that that we can make that connection to, because nowadays they won't get much bigger than they are, right? The universe is now so puffed up, and there's not that much material left in order for them to just grow to a trillion masses, the mass of the sun, right? Yeah, there's just not enough mass. So we're sort of getting to the cap of how big they can be.
That's excellent. Thank you very much. That's all the questions, unless anybody has anything else they want to chuck them in right now. But if not, maybe we can catch up with you after the meeting for the chat then.
Yeah, that's great. Thank you very much.
Thanks so much, and I'll hand you back to Rich and Pete. Thank you.
Juan, thank you very much. That was a fascinating and excellent talk, and I thought it was very interesting how you sort of gathered together all these technologies to help you in your field of research. And I must admit, thinking at the end, it almost asks more questions than it answers in a way, really, with the sort of black hole research. But it's yeah, a great talk, and thank you very much for opening the 2022 talks and presentations with that. It was a very interesting talk. Now we've got a very we've got a tumbler here for you, and I'll just show you it in the camera if you can catch that, as we hand one of these out to everybody who gives us a talk and gives us the pleasure of their company and time and research. So it's we've got your address, so we've got somewhere to send it to you. So thank you very much for your presentation, and it was a very enjoyable and entertaining talk. Thank you very much, Juan. And,
thank you for having me.
Not at all. Okay.
Thanks for that, Rich. So Juan, thank you very much. Really interesting. I said there's so much we don't know about black holes still, isn't there? And be interesting to see what comes up in the future. Right. Okay. As I say, we'll go to the break now. But just before I do, I'm going to ask you to hover over your raise hand button. Would anybody, if the weather holds, now by me saying this, I can guarantee this is going to remotely start the cloud machine. If the weather holds, would anybody be interested in doing a bit of observing tomorrow night at Lambride? If so, put your hand up. No one yet. No one yet. No. Okay, we got a couple of people. Right. Okay, we got a couple of people interested to actually go out. So what I'll do is I'll send an email out tonight, and we'll do the normal registration so we keep within the COVID rules. It wouldn't have to be very late because it's getting dark by about 4:30, so we could start by about around at 5 o'clock if we wanted to, just for a couple of hours. Bring some binoculars if it's clear, but I'll put all this in the email. I'll get it out later on before we finish, and then we'll get the registration done. Okay. Right, so what we're going to do now is we're going to go off to our normal 10-minute break. The chat room is back open, so you can have a chat with everybody here and wish them all Happy New Year's and the likes. For those of you who are watching this in the future on YouTube, I'm going to find my own little black hole, fall into it, and I'll be back with you in about less than a minute. Okay, so from me and everyone else, we'll go to the break and see you in 10 minutes. Bye now. Okay, what we're going to do, come on here, Okay, what we're going to do now is have a look at Alan Tuff's image of Comet Comet Leonard. Alan took this one remotely from the eye telescope down in New Mexico. That was back on the 3rd of December. As I say, he had a cracking image there. You've got M3 in the image as well, and you can see the extent of the tail running down through here. Absolutely stunning image, Alan. Well done for getting that through to us. I've not checked any of the members' photographs at the moment, whether any came in. I don't have time tonight, but if any new ones have come in at all, I'll get them in for next month. So what we'll do now is we'll head over to Stuart for the space news. Over to you, Stuart.
Okay, you have to clear your screen.
Yep, sorry, mate.
Okay. All right, welcome everybody. Welcome to Space News. And it's for January, it's 2022. And I've selected a few topics and events that happened in November and December, because we didn't have a Space News at the December's meeting. And there are a few of the items I've selected. I'm just the one, NASA's IXPE, second from the bottom. Juan may have a comment on that, because that's to do with black holes, but I haven't mentioned a lot of detail about it. I just mentioned the mechanics of the rocket system. So Spin Launch. Spin Launch is a California-based company, and it's developing a rocket launch system that uses kinetic energy as its primary method to get rockets off the ground. It uses a vacuum-sealed centrifuge that spins the rocket at several times the speed of sound before it is released. And the rocket only turns on to the more conventional propulsion, chemical propulsion, when it's well on its way to orbit. It performed its first test flight from the New Mexico base on the 22nd of October, but it didn't report it till later on. And Spin Launch has kept pretty quiet about its progress since its company was founded in 2014. It's part of a group of firms trying to reduce the costs of launching. And Spin Launch suggests that reducing fuel costs is one key barrier to affordable spaceflight. It also reduces the size of the rocket because it doesn't have to carry so much fuel to get off the ground, and therefore makes more space available for equipment, or makes a smaller, less heavy rocket. Other companies are doing a similar thing, like 3D manufacturing, like Orbix, and some are using reusability of key launch systems. For the first test flights, Spin Launch used a suborbital accelerator at 1/3 scale. The scale accelerator is more than 300 feet tall, roughly equivalent to the Statue of Liberty's height. The accelerator, after running the projectile through the vacuum chamber of a rotating arm, pushed the 10-foot rocket aloft from the Spaceport America in New Mexico at roughly 20% of the accelerator's full power capacity. This will enable them to evaluate flight trials with it, and they can adjust the launch speed depending on the size of the rocket and the weight of the rocket. So we see that's the rocket attached to the spinning arm, which it accelerates. And this is a more diagrammatic effect for how it's launched. As you see from one, the spacecraft is loaded into the Spin Launch suborbital accelerator, and that's vacuum sealed. The rotating arm spins using kinetic energy, and it carries a greater payload because less space is needed to hold the rocket fuel. And after launch, it reaches a particular orbit and then returns to Earth. It's got to carry out further trials with different size rockets. It was planned to have one in January, that I could, before the meeting, I couldn't actually get any information on its next launch. It said there was no video taken of its launch, unfortunately, but I was hoping that they were going to get a video of the next launch. Another small company setting up and hoping to get into the market for rocket launches and small satellites was Astra. And for those that saw Space News last time, it did a peculiar launch. It had 3 engines, one of which failed on ignition, and it drifted off sideways and went off until it used up enough fuel to reduce the weight, and then went airborne, but didn't reach its orbital height. Well, it's actually achieved that now. And what I thought I'd show you is, hopefully it'll come up, is it actually doing its launch. So it did work, and they're hoping again to get what they're saying is a daily launch cadence of by 2025, which is quite an ambition. The company was only founded in 2016, and it aims to procure a large portion of the small satellite launch market. The next area is another small company setting up, a company called ThrustMe, has successfully tested in orbit a new electric thruster that blasts out iodine. The findings of the test are detailed in the 18th of November issue of the journal Nature. And this is a milestone that could help lead to significantly smaller, simpler, and cheaper high-performance engines for satellites and spacecraft. Conventional rockets, as you obviously know, use chemical reactions to drive propulsion. In contrast, electric thrusters produce thrust by using electric power to accelerate propellants, such as electrical charged ions, away from a spacecraft. Electric propulsion generates much less thrust than chemical rockets, making it too weak to launch a spacecraft from Earth's surface. But the thrusters are highly efficient at producing thrust, given the small amount of propellant they carry. This makes them very useful for spacecraft that are already in space. Currently, xenon gas is the propellant of choice in electric thrusters. However, xenon is rare. And currently, xenon gas is 1 part per 10 million in the Earth's atmosphere. It is also expensive at about $3,000 per kilogram. And moreover, the gas requires bulky pressurized tanks, as well as complex networks of pipes, valves and pumps to shuttle it around the propulsion system. Therefore, an alternative that's been explored is iodine. And that's been looked at over the last 20 years, is the same element often packaged with table salt and used as an antiseptic. Iodine is cheaper and more abundant than xenon, and can be stored unpressurized as a solid that changes directly into a gas when heated, potentially enabling significant miniaturization and simplification. Previous research has shown electric thrusters using iodine can prove more efficient than ones employing xenon in ground-based tests. However, iodine presents challenges of its own when it comes to propulsion. For example, iodine is highly corrosive, posing a potential danger to electronics and other systems on board spacecraft. In addition, vibrations during launch and spacecraft motion, once it's in orbit, can make solid iodine break into pieces, which may damage the propulsion system, among other problems. Now that scientists have for the first time launched an iodine-based electric propulsion thruster into space, it showed that it can propel a spacecraft in orbit. The ThrustMe states that the following company studies iodine can be safely used in space, bringing an option for propulsion system aboard even the smallest spacecraft. And the new electric thruster, NPT-30, which is shown there as a ground test, is 4 inches by 4 inches by 4 inches and weighs 2.6 pounds. And it has served the propulsion system for a 44-pound CubeSat, which was in the operated by the rocket operated by the Chinese satellite company Spacity, which launched into space on a Long March 6 rocket on the 6th of November 2020. Ground radar stations confirmed that the NPT-30 helped the miniature satellite maneuver in orbit, and the thruster let out puffs of iodine that cumulatively boosted the CubeSat's altitude by more than 1.8 miles. And the new findings show that iodine is not only a viable propellant, but can also achieve nearly 50% more efficient propulsion than xenon because of the factors, such as how iodine is easier to electrify than xenon. And the company has opened a production line for these new thrusters and has already delivered more than 10 of them to satellite manufacturers worldwide. To deal with the problem of corrosion, ceramics and polymers were developed to protect metal compounds within the satellite to keep the iodine from shattering. It was strengthened by embedding the iodine crystals in porous ceramic block. And Thrust may have stated they have an open marketing of this iodine and make it available for use, and have not patented it such that it prevents anyone else developing it further. And they look forward to other companies developing it. They're also saying it would be useful for SpaceX's Starlink mega constellation for maneuvering the Starlink satellites in terms of impact avoidance with other satellites, and also for repositioning. And for longer term, they're looking at larger SpaceX type rockets to be able to use the system as well. Russia's anti-satellite missile test which was on the news. I should imagine most people heard about it. On the 16th of November, they blasted out a decommissioned Cosmos spy satellite into more than 1,500 pieces of space debris. And this caused a few problems. This is before, on the left is before, and on the right is after the impact of the missile that took it out. The 7-person crew of the International Space Station awoke with an alarm and had to move into their transport capsules for the period that the ISS was in the region of the debris cloud for several times over following the hours, according to NASA, that the debris was there. Ultimately, the 6th event ended without any reported damage or injury to the ISS, but the crew's precautions and the NASA's administrator's stern response to Russia were far from an overreaction. Space debris like the kind created in the Cosmos breakup can travel at more than 17,500 miles per hour, and the size of a pea can cause quite considerable damage. The other thing that was affected was the European Space Agency solar mission to take the closest ever images of the sun. That was actually doing a very close fly past of Earth to move it into the correct position to get to the sun, and that had to be monitored very closely from the ground. And James Webb Space Telescope, one I'm sure most people have seen what has happened to this. And what I do show here is the launch, hopefully. That's what, after years of technical delays, funding issues, and a pandemic, including a delay during the final preparations for launch, the James Webb Space Telescope launched on the 25th of December, a good Christmas present for someone, from ESA's launch site at Kourou in French Guiana on board the Ariane 5 rocket. It will take a month to get to its destination, which is a stable gravitational location in space known as the second Lagrange point, which lies about 930,000 miles from Earth. It will orbit the sun from this point, and this point is in space near Earth that lies opposite from the sun, which will allow the telescope to stay in line with Earth as it orbits the sun. Several other space telescopes have used this point, including the Herschel Space Telescope and the Planck Space Observatory. After launch, it will spend 6 months in a commissioning period to ensure its complex mirror unfolds and that all the instruments are ready for observation. This will include, for example, calibration, sun shield and telescope deployment, instrument turn on, and telescope alignment. And I think it's just got finished its sun shield alignment and is moving on to its telescopes at the moment. The James Webb Space Telescope is an infrared space observatory, and according to NASA, it will focus on 4 main areas. It's an international collaboration between NASA, ESA, and the Canadian Space Agency. This is just some of the data around it. Launched 25th of December, cost 10 billion at time of launch. Will orbit the sun. The mirror size is 21.3 feet across, and the sun shield is 69.5 feet by 46.5 feet, and it's 14,300 pounds. And that's an outline of what the how the components fit together. One of the most difficult parts, I understand, seeing on television is actually getting out the sunshade. It'll focus on these areas: first light in the universe, assembly of galaxies in the early universe, birth of stars, and the protoplanetary systems. And it's assumed it will work together with Hubble Space Telescope in the first few years, while Hubble remains in good health. SpaceX bankruptcy or Starship. That's a picture of the November the 12th launch. On the 17th of November, Elon Musk described a dire situation with SpaceX's development of the Raptor rocket engines, which are required to power the company's Starship rocket, in a company-wide email, with Musk adding that SpaceX faces genuine risk of bankruptcy if they cannot achieve a Starship flight rate of at least once every 2 weeks next year. However, Musk replied to a tweet about his comments with some added context, noting that bankruptcy for SpaceX, while unlikely, is also not impossible, especially if the global economy suffers a downturn before the company can get its Starship program up and running. However, if SpaceX really is staring down potential bankruptcy, at least it won't be the first time, because it had the same problem with Falcon 9 rocket early failures until he had a success on number 8, which broke the spell. Musk had hoped to be able to launch the first orbital Starship flight in January or February this year, pending regulatory approval by the FAA, as well as technical readiness. The Federal Communications Commission announced on the 9th of December that the test flight is cleared for liftoff, starting on the 20th of December. But SpaceX still needed FAA's approval to move forward with the mission. And unfortunately, SpaceX Starship is now grounded until March, as the FAA has changed the date of the environmental review to the 28th of February, when it was previously set to be completed by the 31st of December last year. Thus, SpaceX Starship cannot launch until the review is completed. The assessment is looking at environmental impacts of SpaceX's initial mission profile and reviews debris recovery, local road closures in Boca Chica in Texas, where the firm's launch site is located, and some other issues. SpaceX wants Starship to be fully reusable, with both the rocket and its booster capable of landing after launch and to be recovered for future flights. SpaceX's Falcon 9 rockets are partially reusable. The company can regularly land and relaunch the boosters, but not the upper portion or stage of the rocket. Although not stated by the FAA, the delay may be due to one of SpaceX's previous test flights of its Starship SN8 that traveled about 7 miles into the air and then exploded on the launch pad in what Musk called an awesome test. SpaceX eventually launched SF9 for its first high altitude test, but the massive rocket was unable to maneuver into the vertical position before landing on the launch pad and exploded upon landing. And to perfect the rocket, SpaceX plans to conduct several test launches over the next few years, all of which will require a permit or vehicle operator license from the FAA. And just to finalize, the Starship program aims to develop the vehicles for the interplanetary travel of cargo and humans to the moon, Mars, and beyond. NASA has awarded $415 million for a private space station. On the 22nd December, NASA announced that it has awarded 3 funded Space Act agreements for private space stations valued at a total of $415.6 million. The money is split almost evenly among 3 US companies leading each project: Blue Origin, Nanoracks, which I find not a very useful name, and Northrop Grumman Systems Corporation. The ISS is currently approved to operate only through 2024, and NASA has long argued that the facility will be safe to occupy until at least 2028. And the NASA Administrator, Bill Nelson, was endorsed keeping the station running until 2030. That's Blue Origin's attempt at the space station, and it's all 3 are part of NASA's commercial low Earth orbit development program and were given to companies with many years of experience. But whether the company's projects will be ready in time and when the ISS program ends will be open questions as NASA begins to manage the transition. Orbital Reef, which is that one there, a Blue Origin and Sierra Space-led initiative, plans a sort of mixed-use space business park, but it's NASA's words, catering to users around the world in the latter half of the 2020s. Users will include government, commercial, and industry customers. Planned features include reusable space transportation and advanced automation, the latter of which was not widely available when the ISS was being designed. The Nanoracks-led station is Starlab, set to launch in 2027, and this station should host 4 crew members, double NASA's requirement, and have a George Washington Carver Science Park with departments in biology, plant habitation, physical science, and materials research. Northrop Grumman's design, NASA did not disclose a name for the system in the agency's press release, will include a base module and capabilities in sectors including space tourism, industrial experiments, science. Will have several docking ports for expansion possibilities in areas ranging from artificial gravity facilities to laboratories to crew habitats. The companies will have until the 2025 to formulate and design their destinations, as NASA terms the new commercial space stations. Then will come a second phase, including certification for crew member use, which will lead to purchase service agreements. And NASA said a press release concerning the contracts will be forthcoming. The newly awarded contracts are separate from a call for proposals that NASA issued in 2019 to add commercial modules to the ISS or build separate commercial stations called free flyers. NASA selected Axiom Space for docking, port for a docking port element in January 2020, but by that August halted the solicitation process without offering further details, according to Space News. Axiom plans to launch its first modules to the ISS in September 2024, then loft 3 more over the next 3 years. The company's 4 modules could then detach from the ISS and become a free flying station. There are many issues with the current ISS, including the Russians' concern and maybe developing their own space station. This is the one I don't know whether Juan may have some information on, but this is the NASA's Imaging X-ray Polarimetry Explorer. On the 9th of December, NASA launched a new mission named Imaging X-ray Polarimetry Explorer, or IXPE, on board SpaceX's Falcon 9 rocket. That's it being launched. It's a joint effort of NASA and the Italian Space Agency. The mission will study the most extreme and mysterious objects in the universe, supernova remnants, supermassive black holes, and dozens of other high-flying objects, high-energy objects. Sorry. The mission's primary length is 2 years, and the observatory will be at 600 kilometers altitude, orbiting around Earth's equator. IXPE is expected to study about 40 celestial objects in its first year in space. Why is it important? Well, we'll just see what it looks like. It carries 3 state-of-the-art space telescopes, and each of the 3 identical telescopes hosts 1 lightweight X-ray mirror and 1 detector unit. They will enable observation of polarized X-rays from neutron stars and supermassive black holes. By measuring the polarization of these X-rays, it can be studied where the light came from and lead to the understanding of the geometry and inner workings of the light source. And this new mission will complement other X-ray telescopes, such as the Chandra X-ray Observatory and the European Space Agency's X-ray Observatory and the XSM Newton mission. And that's an image of what it looks like. And why is it important? According to NASA, IXPE's polarization measurements will help scientists answer questions such as, how do black holes spin? Was the black hole at the center of the Milky Way actively feeding on surrounding material in the past? How do pulsars shine so brightly in X-rays? And what powers the jets of energetic particles that are ejected from the region around the supermassive black holes at the center of galaxy? I'm sure Juan will have a response to some of that. And finally, I'll just show you that's the IXPE being set up after its launch. Right, and very finally, when you're living on board the International Space Station, you can't just whip out the Uber Eats app and get your favorite pizza delivered into orbit, or can you? On the 11th of December, Uber Eats announced it had made its first food delivery to space, but it wasn't anything like the normal delivery. Instead of sending a driver to swing by a restaurant and take a meal to its destination, Uber Eats used Japanese entrepreneur Yusaka Masawi, a space tourist visiting the ISS, to deliver a brown bag Uber Eats brown bag and a selection of ready-to-eat canned Japanese foods to the ISS crew. And the delivery included boiled mackerel in miso and simmered chicken with bamboo shoots. There he is with his delivery bag. And that's the end. I nearly always get a cold when it comes to these meetings.
I bet they're really happy about having mackerel on the ISS opened.
Yeah. Right, that's me. 2 minutes. Yeah, I was doing something about my cold every Friday. I seem to get a cold.
Right, brace yourself because there's a question coming, Stuart. I think.
Oh, no.
Ask a question. Oh, what do you mean? No.
Donna needs to be here to answer questions.
For the first time in living memory, we've actually got a question from the Space News. Although I do have, if I might make one comment, because obviously previously with Sigma, I've done a number of Hubble presentations. I think the first one was something like 2009. And we talked about the James Webb Space Telescope being the successor. James Webb was supposed to launch in 2007 at a cost of $500 million. So it's about 14 to 15 years late, and it's 20 times the budget. And NASA are only actually expecting it to be in orbit for about 10 years. So that's at $1 billion a year. So yeah, I think that's a fairly expensive way. But as we spoke about earlier on, it's hopefully going to complement Hubble, but maybe not looking at the black holes that Juan was mentioning. We do have a question from Bill Graham. Stuart, spin launcher. For high-speed launches, the radial load on the rocket must be pretty significant on the rocket structure and payload. Does this make for a heavier rocket? And I suspect that probably means, does the rocket have to be heavier to survive all of the extra forces? So are you, in effect, almost like you offset the lack of fuel, but have to make the rocket stronger to survive the launch?
It's a good question. I don't have the I tried to get some more detail, but I didn't have the actual all that detail. I was waiting for the next launch, which they may have given a video and some information. But it's a good question because it's going more than the speed of sound now, 2 or 3 times the speed of sound before they get it to launch. So
an interesting idea, and thanks for the question. But yes, I suspect it may well have to be
strengthened to
survive those extra forces. I think obviously because during a standard rocket launch, those forces are increasing progressively, whereas a spin launcher looks like it pretty much comes as one big kick up the arse before it then gets launched.
Yeah, you're right.
Anyway, thank you. That's the one question. Thank you very much.
Okay.
Right, Mick, just before you jump in, when I put up the members' photos, I realised that was last month's. I hadn't uploaded Alan's new one. And also at the same time, that's the phone call, was Tim's on the phone. He sent through a photograph of me. So bear with me 1 second. I'm going to go spin around this black hole and get a bit of time travel and go backwards to the members' photos, and I'll come back to you in a minute. I'll just share these with you. Right. This is the photograph that I meant to share with you. This is Alan Tusk's latest one from Nambia. It was taken on the 27th of December using a 200mm scope, the eye telescope down in Nambia. And I think this is just as it was starting to break up as well, because you can actually see bits coming off the back of here. He said, unfortunately, he couldn't do any mosaics to actually give you the full length of the tail, but as you can see, absolutely stunning image again from Alan there. As I say, that's Comet Leonard on the 27th of December from Nambia. I'm sure it's Nambia. Yes, it is. And also while we were there, Tim sent through a photograph from a friend of his down in Falklands. So we're not doing anything local tonight. So I'm looking over here, but I've got these on my laptop, not on the main screen. So give me a second. This should come through, I'm hoping. Stop share and reshare again. Should we come back in a second? There we go. This is this was from a friend of Tim's, Amy Lupton, who is an RAF photographer, and she took this pic on the summit of Mount Harriet in Eastern Falklands. So 36-second exposure f4 at ISO 3200, and as you can see, it's showing up a stunning arc of the Milky Way all the way through there. So this is the southern part of the Milky Way that we don't actually get to see from here. in the Northern Hemisphere. But thanks, Tim, for sending that through to us. So we got a couple of other images to look at, and we'll get on now with your bit then, Mick. I'll stop the share.
Thanks, Pete.
Excuse my back.
I'll just finish the video. Right, stuff's delirium now, hopefully.
Yep, got it.
Excellent. Okay, good evening and Happy New Year to you all, and welcome to my January 2022 edition of Sigma's Muddy Sky at Night. First, let's have a look at some high-flying, low-energy objects for a change, Stuart, otherwise known as moon and planets. So currently, the moon is approaching its waxing crescent. It's approaching its first quarter on the 9th. Nice. It's looking great at the minute in the blue sky. And this is tomorrow evening, so how you should see it. So just after sunset, you'll see Jupiter, no problem. Saturn a little bit later, and you're probably going to have to get a pair of binoculars to try and possibly have a look at Mercury. I've not tried it myself, but obviously make sure the sun has set before you put your binoculars anywhere near that direction, because it will cause you permanent damage. So just be very careful. So for most of the month, Mercury and Venus, the two inner planets, are going to be lost in the twilight. If I take the ground away, we can have a little look to see where Venus is. It's just vanished. Worked in rehearsals, but anyway, it's in there somewhere. There you go. And you can see Mars has just set before it, so that's going to be a morning object rising before the sun comes up, but that's going to be lost in the twilight as well. I'll put some lines on, and Mars is going to be moving from Ophiuchus through Sagittarius, so the viewing of Mars is just going to be worse over the next couple of months, I would think. Let's get the ground back. And so as I say, Jupiter, nice and bright in the evening sky, a magnitude of -2.1. By the end of the month, it's a good time to get a good look at that now, because by the end of this month, it's going to disappear from our view up until late May. Capricorn as well, Saturn and Capricorn is also pretty much too close to be easily visible, but it is still visible at the minute. Moving to the 11th, let's make it a bit darker so we can get a bit better contrast. There we go. So moving to the 11th, Uranus is going to be 1.5 degrees to the west of the moon, and that resumes direct motion in Aries on the 22nd of January at a magnitude of 5.7, and Neptune is in Pisces at magnitude of 7.9. To the 13th. Through the 12th to the 13th, the moon is going to be passing, as you can see, the Pleiades, and then just to the north of Aldebaran. Moving towards the 17th, it's going to be to the south of Pollux, and as it moves on through the month, I'm going to have to come a bit later in the evening to show you. It's going to be heading 19th, 20th past Regulus at the base of Leo there. So that's the moon and the planets. Let's have a little look at some deep sky winter objects. So let's ease into it. I'll go back to this. I'll go back to tonight. 2240. That should be good enough. Around to the south. So let's ease it into the tour by locating the brightest star in the entire sky, Sirius, the dog star. The alpha star of Canis Major, the greater dog. And although it doesn't get very high in our winter sky, once you see it, there's no mistaking it. Shining brilliantly at a magnitude of -1.4, it overshadows even the neighbouring bright stars in Orion there. which we'll come to shortly. So our target within Sirius's domain is Messier 41, a sparkling open cluster. It's easy to locate, just head 4 degrees south of Sirius, around about here. Yep, just got it. In fact, I've done it again. I've managed to get right on the brightest star of it. So, get some information for you on the corner. So M41, around 100 stars, can easily be found with a pair of 10 by 50 binoculars. A small to medium aperture telescope can reveal 30 to 50 stars scattered across an area slightly larger than the full moon. So striking cluster due to the high number of bright stars and a sprinkling of red giants for a nicely contrasting splash of colour. The brightest star in Messier 41 is magnitude 6.9 HIP 32406, which is the one I just happened to click on earlier. A class K3 yellow-orange giant with a luminosity around 700 times that of our Sun, and that marks the centre of the cluster. So next we're going to take that away. Next we're going to head up to Monoceros, and we're going to head to the Rosette Nebula, NGC 2244. It's quite easy to find. You can either go straight up from Sirius, or another way of finding it, find the red giant Betelgeuse, or Betelgeuse, in Orion, at the top left there. And looking to the west, east, east, wrong way around. Anywho, left. This next bright star, you find that, and then just come 2.5 degrees down, and there we have, it's centered for you, we have the Rosette Nebula. The Rosette is one of the best emission nebulas in the entire sky. It's a huge, intricate, wreath-shaped cloud of ionized hydrogen gas that's a stellar nursery, like the nearby Orion Nebula, which I'll come to shortly. It has multiple NGC destinations, which I'll put up here, so you can see there's a few of them around here, and these arise from visual observers seeing these back in the 19th century, and they catalogued different parts of the nebula that they could see at that time. Obviously, this was the days way before the era of photographic plates, where it could pick up more information on the photos. Looking at some of the fantastic images of it shot these days, it has to be right up there as one of the treasures of the winter sky. If you've got access to a dark sky observing site, wait for a moonless and transparent night, and then with a bit of dark adaptation, you may spy hints of Rosette's ghostly ring of nebulosity, which extends to a full 90 by 90 minutes in deep images, also through a pair of 10 by 50 binoculars or a finder scope. Much easier to see embedded within the Rosette are individual stars from NGC 2244, a pretty and youthful 5th magnitude open cluster, which spans 27 minutes. These magnificently powerful and energetic stars pour out prodigious amounts of ultraviolet light, which have carved out the massive cavity at the Rosette's core. Okay, I'll now move on to Orion. Let's go and have a look around Orion. Quite a few things to see around here. Orion's main stars, as you can see, form like a kind of bow tie shaped, or butterfly. With the two brightest stars being magnitude 0.7 plus 0.7 Betelgeuse, which is Alpha Orionis, which is a red supergiant, and it's actually a semi-regular variable star. And to the southwest corner, we have magnitude 0.12 Rigel, Beta Orionis. This is an incredibly luminous class B8 blue-white supergiant, the 7th brightest star in the entire sky, despite its distance of 860 light years. It's 79 times the diameter of the Sun, yet it's only 21 times as massive. Its output, though, is colossal, shining with the light of 120,000 suns. It has a magnitude of 6.8 white companion, which currently lies 9.4 arcseconds away from that primary star. But to split the pair is a real challenge for a small telescope, as a companion is swamped in the glare from Rigel, despite an otherwise comfortable separation. So there's a little challenge if you want to try and find its companion. So along with Betelgeuse and and Rigel, Orion's three evenly spaced central belt stars are the easiest to spot. They make an outstanding target for a pair of 10 by 50 binoculars. They're all magnificent stars as well in their own right. Alnitak, Zeta Orionis, the easternmost line of the three, shines at a magnitude of +2, despite it being 815 light years away. It's actually a great double star for small telescopes, with a hot class O9 star of magnitude 1.9 separated from another class B0 star of magnitude +4 by a challenging 2 arcseconds. The middle star Alnilam, Epsilon Ori, is marginally the brightest of the three, shining at a magnitude of 1.7, despite it being more remote at a distance of around 2,000 light years. So that's compared to 815 for Alnitak. It's a class B0 supergiant that's so intrinsically luminous that it radiates at 375,000 times more than our Sun across all wavelengths, and it's 40 times as massive. And lastly, in the belt, we have Mintaka, Delta Ori at a magnitude of 2.23. So I actually say on there, it's slightly different on my notes. This is a closed binary with a hot class O and a class B component that lie too close together for optical detection. Although there is a 7th magnitude companion that can be seen 52 arcseconds away if you happen to be looking for its companion, so you might be mistaken and find that one. So let's now head back to Alnitak and locate two of Orion's iconic deep sky landmarks, the Horsehead Nebula, Barnard 33, and the Flame Nebula. So the Flame Nebula is a fan-shaped emission nebula, or H2 region, spanning half a degree across, that's being energized by the fierce torrent of ultraviolet light spewing from Alnitak. If you manage to keep Alnitak out of the field of view, a 6-inch telescope can show you two distinct areas of nebulosity separated by a spectacular 3 arc-minute wide dividing dust line. Heading south of Alnitak, the Horsehead Nebula is possibly the most famous example of a dark nebula. Cold, dense clouds of obscuring gas excuse me, and dust, blotting out the light from stars and other objects that lie beyond. It's one of those iconic deep sky targets that's taunted visual observers for more than half a century. It's now seen in wonderful images, especially those wide field ones that also take in the Flame Nebula nearby. So visually it's seen as a small notch silhouetted against the ionized gas of IC434 here. Just missed it. So that a long finger, you can see it's just a long finger of nebulosity. I'll take the lines away. There you go. On a clear moonless night, if you use a hydrogen beta narrowband filter or UHC filter in a low power eyepiece of around a 12-inch telescope, you should be able to see that really well, and it should be seen okay as well through an 8-inch telescope. So now we'll move to Orion's Sword. I'll put the lines back on. So Orion's Sword is another landmark feature in this brilliant constellation. On a clear night at a location free from light pollution, it should be easy to spot the sword. So this is the row here of three belts hanging, 3 stars hanging down below the centre of Orion's belt. I'll tell you what, I'll just quickly put the artwork on so you can get a rough idea of what I'm on about. So there we go. Let's get that back up. Oops, the wrong way. Sorry, just get this centered. So you shouldn't have to look too long and hard to realise that there's a fuzzy patch in the centre of these 3 stars. Let me just, sorry, just 2 seconds. Yeah, this is of course the Orion Nebula. Probably the most popular deep sky object of all. This bright diffuse or emission nebula is an area of ongoing starbirth. A pair of 10 by 50 binoculars opens up a spectacular view, with central area of nebulosity being visible together with Messier 43, which is the one just above it. I'm not having much luck hitting these points tonight. There we go. Messier 43, a small detached circular patch of light just to the north. A telescope in 8-inch class presents the Orion Nebula in a magnificent fashion, its glowing nebulosity displaying distinctly green cast owing to its strong O3 emission and being interspersed with numerous dark lanes. At the core of Messier 42, the Orion Nebula, now I need to get rid of these deep space things to get onto it, lies the, yeah, there we go. This is the famous trapezium, or Theta 1 Orion, a multiple star system named for its shape of 4 young, hot and massive L-type stars in the shape of a trapezium. Now I was looking at this for ages and I thought, how's that a trapezium? However, you need to get your telescope right into this one here. It's going to get a bit brighter, you might need your sunglasses. And that splits into the trapezium. So these are hot and massive L-type stars, the brightest of many that are still cloaked in nebulosity, placing them beyond the reach of most amateur equipment. But a 3-inch refractor operating at 40 times, you should be able to split these into its 4 components, and they're actually named A, B, C, and D, imaginatively. Oh, right. The sword's northernmost star, which is this one here, is actually the wide stellar pairing of 42 Orionis, which I just happen to have landed on. And the one next to it, 45 Orionis. So these are young, massive, energetic stars forming part of the Orion OB1 Association, as they're known. And these are embedded within the brighter part of the well-known imaging target, the Running Man Nebula. It's quite difficult to make out on this stellarium image, but these are like arms here, that's the head, and these stars are kind of down this leg here. It looks like the shape of a running man. So within this 29 by 20 wide reflection nebula are striking dust lanes located, yeah, I just said, just to the north of 42 Ori. There's an attractive gathering of stars you maybe noticed just to the north again. This is the Coal Star cluster. A fine sight, again through a pair of 10 by 50 binoculars. So you don't have to go buying any big massive telescopes to catch a lot of this stuff. The southernmost star, which has been pointed out as that one, Iota Orionis. if you go on that, you see a multiple star system sitting down here. And finally, I'll come back out of there. If any deep sky object can follow those little gems, it has to be the magnificent Messier 45, the Pleiades, and Taurus. So to find that, you have Betelgeuse here. Go up to the right, you have Aldebaran in Taurus, and you'll notice this little fuzzy patch, but if you look at it and your eyes are adapted long enough, you'll be able to see like a little mini plough, and this is the Pleiades. The individual Pleiades stars are known as Pleiades, and they're named after the 7 sisters of Greek mythology together with their parents. I won't start going through them, I'm pretty sure you can read them all from there. Most observers can spot 6 stars from suburban skies, with a 7th at least visible from a rural site. It's a spectacular sight through a pair of 10 binoculars, it really is. An 8-inch telescope, an 80mm or 3-inch telescope can reveal at least 60 stars, though it might be a challenge to frame the whole cluster, even using low magnification. Modern images are stunning, with the entire field swathed in beautiful and intricate blue reflection nebulosity. The brightest part of this nebulosity surrounds magnitude 4.1 Merope, which I was on. Why is it not? Oh yeah, I'm on it now. So that's the brightest star at a magnitude of 4.1, just saying, and you can try for that nebula surrounding here using a 10-inch telescope. You should get a really good view of that. So that's everything from me for this month. I shall stop my share.
Well done, Mick. This really is a stunning time of the year to go out observing, and I think it's a time of year that gets a lot of people hooked as well. You know,
yeah.
The first time you ever see the Orion Nebula is just a wow moment.
Yeah, it is.
It really is. So let's say with that, don't forget we got the Sigma telescopes to hire. Any members can hire the telescopes. We got the 6-inch Dobsonian, Helios Dobsonian, and Skywatcher Dobsonian, and the 3.5-inch Helios refractor. So if you want them, let me know, or let Rich know, because he's got the Dobsonian at the moment, and we can get it signed out to you. Just a £5 hire fee to cover costs, and away you go looking at them wonderful objects. As you may have read in the newsletter, the club has been gifted a large amount of astronomical equipment from a lady called Helen Pollock. The equipment belonged to her late husband, Grant Fay, and it actually includes a 2.7 meter pulsar dome, to name just one of the many, many items. I was talking to her the other Sunday, and the list seemed to get bigger and bigger than just what she sent through to me and what I've put into the newsletter. We are in very early stage at the moment, just to see, going to have a look at the pulsar dome, and we'll have to take it down and get it transported. We'll store it for a while we find somewhere to actually erect it. This is if all this equipment is any good to us. But obviously we will be looking for help from club members. If there's anyone out there want to give us a hand to do this, just let me or Rich know. Let's say just to take it down, move it, store it, and put it back up again, and moving all the other kit as well. Thanks to Mike Reed, who has already put his name forward for this one. Let's say a full list of the equipment is in the newsletter. If you haven't had a look, go and have a look. We got a busy time ahead of us getting this lot sorted. Probably won't be ready for this season, but we may have something up and running for the 2022-23 observing season. Returning to physical meetings, we are looking and hoping and praying, for those of you who pray, to go back in April. Okay, we got a lot to do yet. We got to do a dry run, see what we can do, see how many chairs we can fit in. But I've already put our names forward to actually be for us to be in the large hall, so we can distance if we still need to distance. But fingers crossed, come April, we will be back in the hall. Okay. Don't forget Sigma on YouTube. If you came in late on this meeting, it'll be on YouTube for all the members. The link will go out soon. All previous meetings are there as well. So if you want to catch up with anything you missed in 2021, just pop over to there. Outreach. We have started up the outreach program again. So if you have any clubs or societies that are looking for an introductory talk on astronomy, let myself or Rich know once again, and we can offer it on Zoom preferably at the moment, but possibly can do in person if all the regulations are sort of adhered to. Okay, but if there's any clubs out there you are members of, other clubs that want to talk, a speaker, just let us know. We can do a nice introductory talk on astronomy. Don't forget to invite a friend. As I say, renewal has just started, so if you have that friend who's, oh, I'd like to come along to the club, let them know and give them Mick's email, or give their email to Mick if you're allowed to, and he'll send out the membership forms. Okay, the more people we got in the club, the cheaper we can keep it for everyone else. Okay, so the members gathering on Zoom, Rich will be putting that in the chat any moment now, I'm sure, if he hasn't already done so. He already has. Well done, Rich. So once we close this down here, if you just click that link, it should take you straight over. Any issues at all, the link is in the newsletter and in the newsletter email. Just take a note of the meeting ID and passcode as well that's in the chat there, along with the link, just in case there's any issues getting in. It shouldn't be. It takes a couple of minutes to shut this one down and then open the other one up, but we'll see you over there and for a bit of a natter and maybe a little drink and whatnot. Okay, don't forget, if you've got anything from me, let me know. As I've always said, it's your club, not my club. We'll do what we can to make things best for you. I've already sent out the registration email for tomorrow night, so if you're interested in coming along to Lampride, if the weather stays good, reply to that so we got a list of names, and then we'll send out a go, no go email sometime in the afternoon once we've decided whether the weather is going to be any good or not. Okay, but don't go going down there until you know we're actually going to go for it. Okay, that should be there on your own. Okay, so the next meeting is on Friday, February the 4th, from clouds to the crust, and from clouds to crust, how we investigate the surface of rocky exoplanets without seeing them directly. And that is with Oliver Herbert from the University of St Andrews once again. With that, I'd like to thank Juan for his wonderful talk there. I'm sure there'll be a few more questions if you pop over in a minute to the chat, the gathering. Rich, Chris, Stuart, for all the bits you do. Couldn't do it without you, and it runs nice and smoothly. It's only me messed up tonight with the members' photos, but that's there we go. If you don't like it, I'll resign. No, I won't. So with that, I'd like to wish you all a happy new year, and hopefully I'll see some of you at the gathering in a few minutes, or maybe tomorrow night when we're observing. So for now, it's good night from me, and keep looking up, everybody. Good night.